So in the previously we stopped when we want to plug in this wave function into our simplified Schrodinger's equation when u approaches infinity. So let's write this again. Our wave function is h of u times e to the negative u squared over 2. So let's take the first derivative. It's going to be first derivative with respect to u minus h times u of e to the negative u squared over 2. And when we take the second derivative, it's going to be equal to this. Now we've done taking the first and second derivative. I won't go too much into the detail of taking the derivative, but you can go into it by yourself. So we want to plug this back into the Schrodinger's equation. So let's do it. So it's going to be dh over du squared minus 2 times dh du times u plus h times u squared minus h e to the negative u squared over 2. So this is the second derivative minus u squared times the wave function. And this is going to be equal to the negative epsilon of the wave function. Now, we can just cancel out e to the negative u squared over 2 because it's on both sides of the equation. So it's going to get us. So you can see again, we can cancel out these two terms because plus this term minus this term, it's just 0. And let's also move everything to the left side. And factor out h on the last two terms. And yay, we get a new equation, a new Schrodinger's equation, where we have the wave function equals to this. So this is our new Schrodinger's equation, and well, we still don't know what h is. So we want to do a power series expansion with h and see what it is. In case you don't know what power series polynomial expansion is, I'm just going to briefly explain it here. It's basically expressing any function as a series of polynomial. So we can just say that h of u is a number times a coefficient times u's first power, and the number times its second power, and so on, so on. The more term there is, the more accurate this polynomial describes the original function. So we can also write this in the summation notion. So it's gonna be when from n equal to 0 to infinity, a of n times u to the n. So we're gonna plug this again into what we previously just found. So I'm going to plug this into the equation again. So first, let's just take the first and second derivative of our h function. The first derivative of our wave function is just going to be the sum from 0 to infinity of n times a and u to the n minus 1. So in our equation, we can see that our first derivative is multiplied by 2u. So we can just do it here. So multiply this by 2u, and this is going to get us 2n times a and u to the n, because u to the negative 1 times u is just u to the n. So now let's take the second derivative. If we take the second derivative, we're going to get n minus 1 times n a n times u to the n minus 2. Now we want to substitute every n with n plus 2. Because since this goes to infinity, and if we start with n plus 2 instead of n equals to 0, it's gonna be the same thing. So we can just plug in every term as n plus 2 and make the whole summation series start at n equals to 2. So this just equal to n equals to 2 to infinity times n plus 1, n plus 2, a n plus 2, u n. So what we did here is just I plus 2 for every n. And this should get us the same thing. Now let's plug our first and second derivative into our Schrodinger's equation here. So it's just going to be equal to the sum from 0 to infinity of n plus 2 times n plus 1, a of n plus 2 times e to the n, because we prove it here. It's equal to this, we proved it. And minus 2n times a n of u to the n. And we set it over here. And plus epsilon minus 1 times h, and our h, remember we said our h is just this. So a n u to the n. And this whole thing should equal to 0. And we can just simplify it a little bit. And we can also combine the last two terms in this parentheses, in these two brackets. So we can just factor out a of n, so 2n plus epsilon minus 1 times u to the n equals to 0. So we get a relationship between the first term and the term after that. So we can see that if we want this to be 0, then we can just say am plus 2 equals to 2n plus 1 minus epsilon over n plus 2 times n plus 1 equals to an. So get a relationship between the coefficient of the term that's two terms after the coefficient between the first term. So for our recursion, if we want it to become 0, then somehow we want the coefficient of the two term after that to be 0 times the coefficient of the two term before that. So it's like, okay, so to visualize it, we have a0 plus a1u1 plus a2u2 plus a3u3, and we want it to terminate at one point. So we want coefficient of this to be 0 of this coefficient, so it actually terminates, and actually this series doesn't go on forever. So if we want to make this 0, then 2n plus 1 minus epsilon has to be equal to 0. And remember, a long time ago, we defined epsilon equals to 2e over h bar omega. So epsilon equals to 2e over h bar omega. So what it really say is 2n plus 1 minus 2e over h bar omega is 0, and if you multiply both sides by h bar over omega, 2n h bar omega plus h bar omega minus 2e is 0, and we can move 2e to the other side and factor out 2n plus 1, and then divide by both sides by 2, so plus 1/2 times h bar omega. So what this tells us is the energy of our quantum harmonic oscillator must have discrete energy levels, and they must be quantized.